Okay, so in the last session we defined the derivative and also found the derivative of the function y equals x squared. Today we're going to find the derivatives, that is, of several other functions, namely y is equal to the square root of x, y equal x cubed, and y equal 1 over x. Okay? So let's do each one of them, and then we're going to see a pattern that starts developing as we do these. By the way, let's just remind ourselves that the derivative of x squared, I'll use this notation, was 2x. Oh, we'll do one other one, y is equal to just straight x. Let's do that one first. So recall the definition, f prime of x, if this is my function right here, is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. That was one of two different forms of it that we had. So let's apply it to this. Since this is my function right here, if you put in x plus h into this function, you get an x plus h out. So you're going to get x plus h minus f of x all over h. That becomes, minus f of x. F of x is just equal to x. And so the x's cancel. We get the limit of h over h as h goes to 0. Again, for anything other than 0, h divided by h just gives you 1. So this thing is just going to be 1. And as h goes to 0, that value will always be 1. So the limit is 1. So now we have ourselves another result, which makes complete sense because this is just the line y equal x, and we know that the slope of that line is 1. So that's good. The derivative of that line is 1 at any point, which is what we should have expected. Okay? Let's try the next one. So now the function that we will look at is, let's do this one. F of x is equal to square root of x. So this is going to be the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. And so to do that one, let's see, how are we going to do it? Notice that we got a bunch of square roots there, and the key to that, if h is equal to 0, we get 0 over 0, which makes no sense. But what we can do is multiply both the top and the bottom by the conjugate. Like so. And we'll get the limit as h goes to 0. What happens when you multiply this out? Here you're going to get x plus h. This one and this one cancel out. And then you're going to get square root of x times the square root of x is going to be a minus x. All times the bottom here, or I should say divided by the bottom. And then notice that x minus x, those things go away. And I forgot my h here on the bottom, so that's still times h in the denominator. So I have h times this in the denominator, and I end up with just h in the numerator. And now these h's divide out. Get a 1 right there. And what happens? See, notice in each one of these cases you have 0 over 0 until you, at some way or another, get rid of that common factor there, that h over h, and now we can evaluate the limit. So what happens as h goes to 0? You're going to get square root of x here, square root of x there. So you have two of them, 1 over 2 times the square root of x. So let's write that one down. The derivative of the square root of x is equal to 1 over 2 times the square root of x. Okay, very good. Let's try the x cubed. Don't lose sight of what we're doing. This thing right here, no matter what the function is, what are you doing? You've got x here. You've got x plus h here. This is f of x. That value is f of x plus h. So in all of these cases, we're doing what? We're taking this value divided by this value. We're finding the slope of the secant line. And then what are we doing? We're taking that as h goes to 0. So we're finding not the slope of the secant line, but the slope of the tangent line at this point right here. Okay? Never lose sight. Never just see a formula there and just see a bunch of symbols. That should when you see that, you should have a picture in your mind of what that represents. So here's our function now. So if we put in x plus h, we're going to get the limit of x plus h quantity cubed minus x cubed, all divided by h. And each one of these involves some sort of little algebraic trick. The hardest part of all these is just the algebra. So here in this case, what we need to do is to multiply out x plus h quantity cubed. I happen to know what that is if you multiply it all out. I won't take time to do it here, but what do? You take x plus h, and you first multiply it by x plus h, which gives you what? X squared plus 2xh plus h squared. And then you multiply that by yet another x plus h. Running out of room. And when you multiply that all out, here's what you end up with. X cubed plus 3x squared h plus 3xh squared plus h cubed. When you multiply all that out. And now what do? We subtract off the x cubed and divide it by h. And what happens? Limit as h goes to 0. Notice the x's cancel out. Then I can factor an h out of the top. If we factor an h out of the top, we're left with 3x squared plus 3xh plus h squared, all divided by h. And now, again, at this point, it's 0 over 0, so it's undefined at 0, but we're just taking the limit as h approaches 0. So for everything right up until 0, this thing is going to cancel with that. And so the limit, you don't care what happens at 0, you just care what happens as you get close to 0. So you can divide those out, and now what happens? As h goes to 0, this goes to 0. Here you have 0 times 3x. So that goes away, and you're just left with 3x squared. Okay? So there's that one. Let's write it right here. The derivative of x cubed is 3x squared. Okay, one more. Here's our f of x. So what's the derivative? You stick an x plus h in here, so that's going to be 1 over x plus h minus 1 over x, all divided by h. Each one of these, that's why I chose these particular ones, each one of these uses a different little algebraic trick, okay? Conjugates, multiplying them out. Here, again, if you just let h be 0, you're going to get 0 over 0, so that's no good. We have to do something to simplify it. The thing you do to simplify it here is to get a common denominator. So if you get a common denominator, what does that mean? The common denominator of the top here would be let's see, common denominator would be this times this. So I'm going to get x times x plus h. So if I multiply the bottom by x, I'm going to also have to multiply the top by x. And here as well, I have the same common denominator. But here I had a 1 over x. I multiplied the bottom by this, so I have to multiply the top by that. So you get that. And now just to save space, I have this over this denominator minus this. As long as you have the same denominator, you can combine them as one denominator, just like if you have 1/3 plus 2/3, you get, add those together, you're going to get 3/3. So as long as the denominator is the same, you just add the numerators. So here in this case, I'm subtracting them. So if I subtract them, I have just this denominator now. And I have this thing minus that thing. And that's all divided yet by h. Okay, that's all divided by h. So how does that simplify? You can see why algebra is important in calculus. If you're going to understand calculus, you need to know how to manipulate symbols. So here, x minus x, those are going to go away. I'm going to end up with a negative h on top, all divided by x times x plus h. And on the bottom, if I want to, I can write this as h over 1. And the reason I write that as h over 1 is because if you have one fraction divided by another fraction, what do? You flip it over this line, and multiply. So that's going to be the limit as h goes to 0 of negative h over x times x plus h, all times 1 over h. And now this thing cancels with this. You have a 1 there, a negative 1. So you're going to get a negative 1 on top. And on the bottom, as h goes to 0, that's 0. So you just have x plus x times x, which is x squared. So there's our final one right there. The derivative of 1 over x is negative 1 over x squared. So let me write these all down for you now and see once if you can see a pattern. Okay, I'm going to write them like this. I'm going to write the derivative of x is equal to 1. The derivative of x squared is equal to 2x. The derivative of x cubed is equal to 3x squared. The derivative of, I'm going to write this as x to the 1/2 power. And the derivative of x to the 1/2 power, I'm going to write as 1/2 times x to the negative 1/2 power. Agreed? That's what this is. 1/2 x to the negative 1/2 power. And finally, the derivative of 1 over x, and I'm going to write that as x to the minus 1, is negative x to the minus 2. Do you see a pattern? Okay, you can turn the video off if you want and just think about it, or put it on pause. But I'm going to go ahead and tell you, here's the pattern. Notice that in all these cases, when we took the derivative, we essentially just took whatever this power was and we brought that down front. The 3 came down front, and then we subtracted 1. Here the 2 came down front, and this is x to the first power. Here we had x to the first power, so we brought the 1 down front, and we could have written that as x to the 0 power. X to the 0 power is just 1. So that's the case. Here we have 1/2, bring that down front, x, you subtract 1, x to the minus 1/2 power. And finally here, x to the minus 1, you bring the negative 1 down front, x to the minus 2 power. Now this is not a rigorous mathematical proof, but it should be somewhat convincing and at least suggestive of the fact. And this is the case, so I'm just going to tell you right now, this is the case, even though we're not going to go through the entire proof of the whole thing. Is here's the result. When you take the derivative of x to any power, doesn't matter what the power is, I'm just going to use r there. It could be an integer, it could be a fraction, it could be an irrational number like pi or something like that. It doesn't matter. The derivative of it is the same as what you saw here. You bring that number down front, and then you subtract 1 from it. So there is the derivative of anything like this. And so, as I say, if you wanted to, you could find the derivative of x to the pi, and that would be pi times x to the pi minus 1. Okay? Might not ever need that in life, but there it is just in case you need it or want it. Okay? So the point is, if this is the function, this thing right here tells you what the slope of this is at any point. This always tells you the slope of this one. Okay? And then that's it for now. Let me do just one more, just for completeness. Remember what the absolute value function looks like? Okay, it looks like that. What would be the derivative of this one? What would be the derivative? Just think of it in terms of slope. Anywhere along here, if we were to take some x and evaluate it, the slope would be 1. So since the slope is 1, that tells you that the derivative is 1 when x is greater than 0. And for anything along there, the slope is negative 1. So the derivative would be negative 1 for x less than 0. And notice what one value is left out. At 0 itself, there is no derivative, which kind of makes sense just by looking at it, because what did we say a derivative was? It was the slope of the tangent line, this line that touches the graph at just that point. And if you have a nice smooth curve like this, something that touches the graph at just that one point, there's only one line that does it. Any other line is going to go through the graph. Let me draw that one more time. Okay, you have a graph like this, say, and you take this point, there's only one line that touches the graph right there that doesn't slice through the graph. That's the tangent line. Looks like that, and that's the slope of that is what we're after. Here, however, notice with that sharp corner there, there's all sorts of tangent lines that hit it at just that point. Here's one right there, here's one right there, the x-axis is one. There's all sorts of them. So there is no unique tangent line at that point. There's no derivative at that point. Okay? So that's kind of an important function just for that reason. Okay, that's it.